So we left off with this example on Friday. We did this top example where we identified the acid, the base, the conjugate acid, the conjugate base. We went through and determined the equilibrium, and we did the mechanism. And I don't think I've I haven't explained what a mechanism is at this point because we're going to the next section dealing with nucleophiles and electrophiles is pretty detailed about that. But I can give you I should give you the definition now since we're pushing arrows. So when we talk about a mechanism, what we're talking about is a detailed description. Right, of how a reaction happens. But you don't use words, you use curved arrows. Right, so in organic, when you hear the term mechanism, that's what it's talking about. It's talking about showing how you got from point A to point B using arrows only, right? I actually still see students in part two, and I'm not knocking them because, you know, part two, a lot of what you do in part two is predicated on what you learned in part one. But when I ask for a mechanism, they write out a paragraph about it. That's not how it works. A mechanism only uses arrows to show how electrons got moved from point A to point B, how new bonds got formed, so on and so forth, right? So let's do the second example. And then we're going to come back to the first example and maybe talk about we're going to do both actually, and talk about the factors that affect the pKa. But the second example will be a little bit clearer. All right, so let's do this. So let's put some electrons in here. This is my base. A rudimentary way to identify the base is to locate the atom that has either a negative charge, right, or the atom that has electrons to donate, right? The difference in a base and a nucleophile, which we're going to talk about in the next section, is so nuanced that there's really not one clear-cut definition about how to identify a base or a nucleophile. But in the case of acid-base chemistry, the base usually is either going to have lone pairs or it's not going to have any protons on the atom with the lone pair. So here, this has lone pairs, but it also has a hydrogen. I'm gonna fix this up so we can actually see that bond breaking. It actually has a hydrogen bonded to it, and it's a highly electronegative atom. So that means that that's going to be this is my acid, right? So when we're doing acid-base chemistry, and the way we show this mechanism is to always start at the base. I think we talked about this on Friday, where the arrow should begin and where it ends, it matters. So my arrow is going to start here, and then I'm going to break that bond and give those electrons back to sulfur, because in an acid-base reaction, when you break the hydrogen bond, the electrons in that bond always go back to the more electronegative atom, right? And this is heterogenic. Just refreshing you. And this bond breaking is heterolytic. All right, so that's how we got to the other side. You can see over here, now sulfur is missing that proton, has a negative charge, and then oxygen picked it up. All right. Question is, which way will the equilibrium favor? What do you think? How can we tell that? How do we predict the equilibrium? What do we need to predict the equilibrium? How do we predict it on Friday?
pKa.
We need the pKa values of the acid and the conjugate acid. There you go, per two, sorry. So somebody look up butanol, 1-butanol. And then somebody look up 1, 2, 3, 4, 1-butane thiol. A thiol is just a sulfur analog of alcohol. That's one of our functional groups. We didn't talk about it, but it's one of our functional groups. If you look at the functional group list that I've provided, or if you look at the functional group list in any book, thiol is going to be one of your functional groups. All right, so 1-butane thiol and then 1-butanol. Somebody help me with those pKa's. Use that iPhone 17. Anybody got it yet? I beat you to the punch. So this is 10.78. At 16, I think. Most of your alcohols are going to range somewhere between 15 and 16 for pKa. All right, so we know those values now. We got 10.78 for butane thiol, 16 for butanol. Which way is the equilibrium going to favor? I know it's Monday. Okay, yeah, thank you, Michael. I just saw that in the chat. I have I found what I found was 10.78, but we'll use the one on the screen, but that's fine too. 10.2, because pKa is kind of measuring it can be somewhat imprecise, so that's fine. All right, now, how do we figure this out in terms of the equilibrium? What do we need to do?
Wouldn't can you use wouldn't butanol be favored because it's the weaker acid?
Yes, that's exactly right. So when you're trying to determine equilibrium or the the position of equilibrium in an acid-base reaction is always going to favor the weaker acid. And we're going to talk more. I'm going to try to flesh that out with this example. All right. So what does that mean? So this is the weaker acid. It has a higher pKa. So if it's on a fulcrum, this is 16 and this is 10 point, I'm going to say 10 and round it up to 10.8. Right. What does that mean in terms of how much better of an acid butane thiol is? Because we can figure that out. And if we know that, then we can use that to describe or to discuss why the equilibrium favors the other side. What was the little formula we used for that? Anybody remember when we talked about acids and how much more acidic one acid is than the other? How do we determine that?
10 raised to the difference in pKa values.
Good, excellent. So 10 raised to the difference or delta pKa. In this case, it's going to be 16 minus 10.8. That's going to be 5.2. Is that right? And I'm putting the absolute value because you can swap the numbers around, but you don't want this number to be negative. It's always going to be positive. So X is 5, oh, not 5.2, 10 raised to the 5th. Can somebody calculate that? What is that number? It's huge, isn't it? Is that 100,000 or 10,000? Anybody got it yet?
That's to the power of 5.2, right?
Mm-hmm. You can round it down to 5 if you want, but it's going to
Okay.
give you roughly the same answer. But go ahead.
I got hold on, 158,490.
Okay. Excellent. All right. So we can say that butane thiol, that's all one word, by the way, is 100, and we're going to round this up. Let's say 160. 160,000 times more acidic. Everybody following? Anybody not following? Say something.
Okay, I have a quick question.
Go ahead.
So that's how we would write like the final answer as far as like explaining the difference. You
Yeah.
would write it in a sentence like that.
Yep. That's exactly right. If you were asked how many more times acidic is blank acid than blank acid, and you calculate it, that's how you would write it out. Now let's think about
Okay.
Yeah, very good question. But now let's think about what that means. So let's say, what do acids do again? So that's butane thiol, and that's butanol. And we're going from here to here. Is that right? Because I'm going from acid to conjugate base. And all this is a fancy term But all this is the acid without the proton that was attached to it. That's all. That's it. It's the acid after it gives up the proton. It becomes the conjugate base. Everybody on board, say something if you're not. Right? So now let's say that this is the conjugate base. Every time let's say every time butanol loses one proton, that happens right 160,000 times for butane thiol. So every time you lose one proton from the butanol, that happens 160,000 times for butane thiol. Does that make sense? So you got 160,000 molecules of butane thiol giving up a proton every time one molecule of butanol gives up a proton. That's what that means in relative terms. Does that make sense or no? Because that's the
Yes,
goal of the goal of the acid is to give up its proton. And if one acid is this many more times acidic than the other, that means that every time a proton is transferred, if the difference is, like in this case 160,000 times different, then every time one proton is transferred from butanol, that happens 160,000 times for butane thiol. That's a lot. And you're talking on a molecular level. All right. So that's why the equilibrium is going to favor the products, because every time you get here, right, that forward reaction is going at 160,000 times the rate of the reverse reaction. So in order to go from here back to here, that's happening once, but the forward reaction is happening 160,000 times. So that's why equilibrium is going to favor the weaker acid, because the weaker acid can't compete going the opposite direction, giving up its proton, if that makes sense. So that's why equilibrium favors that side. And I'm gonna write that out here. We'll say the reverse. The reverse of that process is 160,000 times slower. I'm gonna take out process and put in reaction. Right, so the reverse reaction going back to the starting materials, which are on the left, is 160,000 times slower than going to the right. So equilibrium always favors the weaker acid, and that's why, because the weaker acid can't compete with the acid on the left as far as how many times it can give up a proton to go back to the left. Because you can see that the same thing will have to happen in order to go back to the star materials. The OH will have to give up a proton to sulfur to get back to here. But it happens too slow. All right, questions? Any questions about anything? If you're lost or you tread in water, say something. Because now we can use this example to discuss another topic, which is the factors that affect the pKa. Why is butane thiol so much better of an acid than butanol? And we can do that using let's say this, ask this question then. If you look at the pKa, it's not great. 10 is actually not, it's not a very strong acid, but it's a strong acid compared to the alcohol, right? Stronger. The question is why? So let's answer that down here. What do we look for? Like, how do we determine or predict what the pKa may be? How can we do that? By looking at the atom where the charge is when that when that acid loses its proton. So we can use HIRES, right? So in this case, let's rule out what we can rule out. H is for what? Anybody?
Hybridization.
Hybridization. What's the hybridization state of sulfur and oxygen in the conjugate base? That's on the right side with the charges. Those are your conjugate bases. What is the
SP3.
if they're both sp3, right? So the advantage is not coming from hybridization, right? And there's nothing, there are no vacuum cleaners. I think that's the example we used Friday to suck away smoke. In the terms of electron density, there's no vacuum cleaners around. So induction is not the advantage. Neither can do resonance, am I right? They're both donors, but they don't have acceptors near them. Is that right? So resonance is not the advantage. All right, now we're down to, what's the E for? Anybody?
Electronegativity.
Electronegativity, good. Check the periodic table and tell me which is more electronegative. Remember, the trend is left to right and bottom to top. So it increases from left to right and it increases from bottom to top. So between sulfur, they're in the same group, by the way, in the same column. So between sulfur and oxygen, which is more electronegative?
Oxygen.
Oxygen, good. Right, now let's see if that's an advantage. Right, now we're going to also compare the size because those are two different atoms. So that means it means they're going to have two different atomic radii. Now atomic radius is similar. It increases from left to right, but it also increases from top to bottom. So sulfur is under oxygen. So that means it's bigger. So based on the results, based on what we see, with butane thiol having a pKa of 10.78, butanol having a pKa of 16, and comparing the two conjugate bases, which one would you say is more stable? Because the lower the pKa, the more stable the conjugate base is. So which one would you say is the most stable conjugate base? Right? Think about it in terms of giving up that proton. The proton is not leaving. It's not leaving unless the conjugate base is stable enough to handle that negative charge. Right? So look at the two pKa's up top and tell me which one has the best conjugate base. All the information we've talked about points to this as well, but if you're just looking at, if you want to make a prediction about which acid is better and which one has a more stable conjugate base, you can do that by just using the pKa's also. which acid is stronger?
Butymethyl.
Butanediol, good.
Butane.
Okay. So what that means is that the conjugate base of that acid is more stable. All right. So this is, we can come back down here and we can put that this is the more stable conjugate base. Trying to get to this point right here. So if we say that, and if we look at the pKa, that proves it because it's a stronger acid. But and we say it's the stronger acid is going to have a more stable conjugate base. What can we say about the comparison between the size and electronegativity? Which one do you think is more of a stabilizing factor? Based on everything we talked about up to this point. If the conjugate base containing sulfur is more stable, what can you say? Which one? Go ahead. Which factor is more of a stabilizing factor between electronegativity and size?
Size.
Size. That the whole conversation I'm trying to lead to that point. So oxygen is more electronegative. Sulfur is bigger. So we can say that size is more of a stabilizing factor. Right? Why is that? Why do you think that is? If you watch that size video, the pKa video dealing with size, you can explain that. But why do you think that size is so important? What's the goal of when we talk about stabilizing a charge? What are we trying to do to it to stabilize it? What's the best way to stabilize it? There's a special word that we use. Starts with a D.
Delocalize.
Delocalize. We want to delocalize that charge. Localized charge is unstable. So if we can spread it out some kind of way, that's good. So size allows it spreads the charge out over a greater surface area. So charge is delocalized over a larger surface area. Right, and that factor by itself is the reason why butanediol is a better acid than butanol, because once you get to the conjugate base, the charge on sulfur is stabilized because it's spread out over a bigger atom, which offers more surface area, as opposed to oxygen, which is a little bit smaller atom, but that charge is more localized, right? So that's the difference. Any questions about that? Everybody's quiet today. Well, not everybody, but we're not getting as much feedback today. Any questions about that?
So is butymethyl a stronger acid because it has a weaker conjugate base? Is that
Not
Right.
weaker, not a weaker conjugate base, but a more stabilized conjugate base.
okay?
Yeah. But
And then
go ahead.
I said, and then like the explanation for that would be, so basically what we're doing is just constantly going through hires and figuring out which one is the
advantage.
deciding factor.
Yep. Which one gives the stronger acid the advantage? Now, So was that Kadir? Was that you that asked about weaker versus stronger conjugate base?
Yeah.
All right, let me answer that question. Okay, well, if it's more stabilized, that's a good question. It is in a sense weaker in that it does not want to give those electrons up to pull away a proton from the conjugate acid to go in the reverse direction. So that's a great question. That's a very thoughtful question. So in a sense, yes, you could say that it is a weaker base than the conjugate base of the alcohol, but it's weaker because the charge is more stabilized. So think about like life. Life is like that. The more stable, and I like to talk about this in terms of human beings, the more stable a person is, the less prone they are to go out and disrupt that stability. You know, whether it's go rob a bank, go, pick a fight with somebody, cheat on their spouse, whatever, they don't want to disrupt that. So the sulfur, with it being more stable, is less apt to react. So yes, and I answered that hastily, and I apologize for that. In a sense, yes, it is a weaker conjugate base, but it's weaker because of the increased stability. That's a great question. Very thoughtful question. I don't know if y'all see how we walked this down, but we went through every facet of the pKa discussion. We went through the mechanism. We went through determining the difference in acidity. And then we also went through determining conjugate base stability using hires with this one example, and equilibrium prediction. So let's do some other examples. I think on Wednesday, we're gonna have like a little work day. So we're gonna work through a bunch of these up here. But I want to do this example in the last 10 minutes. It's the same exercise that we just did, but it's on two different acids. All right, so somebody look up the pKa for triflic acid. And then somebody look up the pKa for toxic acid. Just Google it. I think in the announcement, I think I said that we would try to meet in person to, Wednesday. We'll be in room 304. All right, anybody got triflic acid? If you can't find that, you can look up trifluoro. Hold up, this methyl. Sulfonic acid. And this one is toluene sulfonic acid. Anybody got it?
I think the pKa says of triflic acid is
And negative.
it says -15, but does that sound right?
Oh yeah, that's what did that tell you? If we measuring pKa, something that's -15, right? That's not a positive number, it's a negative number. What does that tell you about that acid? What can you say about it right away?
It's strong.
Very strong. compared to anything on the chart, that's going to be like one of your strongest acids. I've worked with triflic acid as a grad student. When you take the cap off the bottle, the vapors react with the water in the air. Like that's how strong of an acid it is. It's immediate. So yeah, pKa is negative 15. Ooh, wrong box. All right, what about toxic acid?
Negative 2.8.
Negative 2.8. We're going to round that up to negative 3. Since the other one is 15. All right, that'll make it easier to calculate the difference in pKa. All right, so the question is, it says explain the pKa difference. Let's do the other questions first, and then we'll come back and explain that. So how much more acidic is toxic triflic acid than toxic acid? We know the formula for that, right? X, we got 6 minutes left. We can do it. It's 10 to the minus what? I'm sorry, not minus. It's absolute value. What is it? Negative 15 to negative 3. As you can tell, they're both very good acids. They both react rapidly and spontaneously with water. It's going to be 12, 10 to the 12th. Is that right?
Yes.
Mm-hmm. Somebody calculate that. 10 to the 12th. What is that? About, let's see, a billion? Is that a trillion? Isn't that right? 10 to the 6 is a million. To the 9th is a billion. So to the 12th will be a trillion. Is that right? So we're going to say that triflic acid is a trillion times more acidic than toxic acid. That's crazy, right? When we see these numbers, they don't matter. They don't mean a lot to us, but they do. They actually mean a lot on the molecular level. What does that mean in terms of, okay, let's go to the next question. What does the answer say about how readily, let's answer this question, how readily the proton is removed from the stronger acid? So the stronger acid is going to give up H plus without a problem. What does that mean in terms of how much more acidic it is or how much lower the pKa is? What does that mean in terms of how it's going to give up H plus based on the answers we have in front of us?
It's be deprotonated rapidly.
Rapidly. It's a rapid, it happens. So let's go back to our other example. How many proton transfers are happening with triflic acid for every 1 proton transfer from toxic acid?
$1 trillion.
That's a trillion. If it's a trillion times more acidic, that means that for every 1 trillion proton transfers on triflic acid, so that's a trillion molecules of triflic acid giving up H plus all at the same time, right? Compared to 1 of toxic acid giving up H plus. At the same time, these other trillion reactions are happening. That's crazy. All right, let's do the next question. What can we say about the conjugate base of the weaker acid based on the answers we have present? The conjugate base of the weaker acid, if the pKa is based on the stability, it's loosely based on the stability of the conjugate base. So it's loosely based on conjugate base stability. So a more stable conjugate base is the result of a stronger acid giving up its proton. A less stable conjugate base is a result of a weaker acid giving up its proton. What can we say about the conjugate base of the weaker acid?
The conjugate base is less stable.
Less stable. Good. Excellent. Less stable. All right. Now we got 2 minutes. And we need to answer the question. Explain the pKa difference. All right. And we can do it. This is triplet acids conjugate base. Let me write this out so it'll be even more dramatic. So we got 3 fluorines out here. This is negative. And then this is toxic acids conjugate base. That's negative. All right. How are we comparing these? Right? Hybridization is not an advantage. The charges on oxygen in both cases. Size and electronegativity are not advantages because the charges on the same atom in both cases. It's on oxygen. So the size difference, there's no size difference. There's no electronegativity difference. Can they both do resonance? Do you see?
Yes.
You see the pattern here, right? It's like an allylic anion. So I can do this and this, or I could have done this and that, right? So I can do resonance. Can I do that over here? Same pattern?
Yes, you can.
Can, right? I can push those electrons either way. So resonance is not an advantage. So what do you think the difference is going to be based on? So it's based on resonance because that's a delocalizing mechanism, right? We can delocalize electrons that way. So we can use resonance, but both of them can do resonance. What's the difference? The difference is here. Those fluorines make one heck of a vacuum cleaner, right? And all the electron density that's on oxygen, in addition to being delocalized by resonance, can also be delocalized by induction.
I have a question.
Go ahead.
So as far as like crossing out the other factors like the electronegativity and size and all of that, how are we able to cancel that out so quickly and just come down to induction?
Okay, great question. Because the charge is on the same atom in both cases.
Okay, so because they're both oxygen, they're both on
oxygen.
the,
So they're both
Okay.
sp3 hybridized. It's the same atom, so the electronegativity doesn't change. And it's the same atom, so the size is not going to change.
okay, got it. Thank you.
Yeah, great question. So we got all this induction from the CF3 group. That's actually a really good group to create induction and polarity. It's got huge induction, right? Plus resonance. On the other side, you have a little bit of induction from the aromatic ring, but not much, plus resonance. But obviously the induction created by the trifluoromethyl group is much more prevalent and much more pronounced. That's why you see that huge difference in pKa, because the inductive effect of that CF3 group is large, very large. So that's a very stable conjugate base. All right, we got to stop. We're 2 minutes over. Other questions? Seems like y'all are getting the hang of this and it's starting to click, so that's a good thing. Other questions?
You said we were meeting Wednesday in Armstrong, room 304. What time?
Same time, 10 o'clock.
Okay, thank you.
Yep. All right, let me stop recording. If there are